All right, welcome to this explainer. Today, we're going to do a deep dive into the Vera Rubin NVL72 platform. It's a system that's really built on this fascinating philosophy of extreme co-design. Okay, let's just jump right in. To really get this, you got to look at how much computing has changed. On the left, that's what high-performance computing looked like back in 2016. A single server was your building block. Now, look to the right. That's today. The entire rack has become one single massive accelerator. We're not just talking about an upgrade here. This is a complete reinvention of what a supercomputer is. And really, it all boils down to this one sentence. This is the core idea. The focus isn't just on the chip anymore. It's about the whole system. The silicon, the networking, the mechanical parts, the power delivery, all of it designed together, from the ground up, to work as one. So what does this new unit of compute actually look like on the inside? Let's take it apart and see what makes it tick. Just look at this thing. The density and the integration here are absolutely insane. You've got 72 compute trays. That's the brains of the operation, sandwiched between these huge power shelves pumping out 220 kilowatts. And then right there in the middle, you see the 9 NVLink switch trays, which are like the system's high-speed nervous system. This isn't just a box with a bunch of parts. It's a complete, self-contained supercomputer in a single cabinet. So you have this incredibly dense and powerful system, but how on earth do you actually build it? Well, the answer is in this crucial mechanical innovation that just changes the whole game. This is how things used to be. This is what's known as the complexity trap. It's just a dense, tangled mess of these high-speed flyover cables. They're super fragile, a nightmare to route, and it made putting one of these together a slow, manual process that could take hours for just one unit. And here's the solution. It's so elegant. The Rubin compute tray is completely cableless. It uses these really robust board-to-board connectors that blind mate, which basically means they just click into place automatically and perfectly when you slide the tray into the chassis. This isn't just about looking cleaner. This whole thing is designed for robots to assemble. And here's the bottom line, the real payoff. You go from a complex 2-hour manual process to a modular, automated one that takes just 5 minutes per tray. 5 minutes. That is how you can actually build these incredible systems at scale. All right, let's zoom in even deeper now, right down to the very heart of the system, the brand new silicon that makes all of this power possible. First up, you've got the Rubin GPU. It's built on a cutting-edge 3-nanometer process, and it is an absolute monster. The key number to pay attention to here is memory bandwidth. It jumps to 22 terabytes per second. Thanks to new HBM4 memory. That's nearly a 3x leap. And for AI, it's cranking out 35 petaflops of compute power. We're talking 35 quadrillion calculations every single second. It's just mind-boggling. And you can't have a monster GPU like that without a CPU that can keep it fed. That's where the Vera CPU comes in. It uses these custom Olympus ARM cores, but its real job is to be the ultimate quarterback, making sure data flows to the GPUs so fast that they never, ever have to wait for it. Okay, so you have these incredibly powerful chips, but that's only one piece of the puzzle. Connecting, powering, and cooling 72 of them in a single rack, well, that is an engineering challenge on a completely different level. The system's nervous system is the new NVLink 6 interconnect. And it uses this really clever trick called bidirectional SerDes. Now, instead of needing one wire to send data and another wire to receive it, this thing sends and receives signals on the same exact wire at the same time. And the results? You double the bandwidth to 3.6 terabytes per second with absolutely no increase in copper. That's just brilliant engineering. And all that high-speed data zips through this, a vertical PCB midplane. The best way to think about it is as the rack's spinal cord. It connects the compute modules in the back directly to the I/O in the front, and it gets rid of yet another layer of cabling, which is great for signal integrity. Of course, all this performance needs a ton of power and creates an incredible amount of heat. To feed this 220 kilowatt beast, the system uses these liquid-cooled copper bus bars to deliver power directly and efficiently. And to get rid of the heat, the entire system is 100% liquid-cooled. What's really cool, no pun intended, is that it's so efficient it can run with warm inlet water, around 45 degrees Celsius, which means in a lot of places, you might not even need expensive, power-hungry chillers anymore. So we've broken down the silicon, the mechanics, the plumbing of the system. Let's zoom back out and see what this whole extreme co-design thing actually gets us. What's the final payoff? Man, The numbers on this chart really just tell the whole story. In a single generation, going from Blackwell to Rubin, we are seeing a massive 3.5 times increase in AI performance. Memory bandwidth is up nearly 3x. The interconnect speed has doubled. This isn't just an incremental step, you guys. This is a monumental leap forward in what we can do with computers.
This generational leap really cements it. The rack, not the chip, is the fundamental unit of AI compute now. It's this incredible convergence of mechanical, electrical, and silicon engineering. And it leaves us all with a really compelling question. With a 3.5x performance leap now on the table, what challenges, what problems that we once thought were impossible are we now finally going to be able to solve?